Hello, on behalf of TAS International, welcome. My name is Peter Rittmeyer. This presentation will give a brief introduction to the FEFE context within MADYMO. Those are the topics to be addressed. We will discuss the two main contexts within FEFE. Those are the characteristic-based contexts and the material-based contexts. Characteristic-based contexts are pretty similar to the ones in MBMB and MBFE, so those will be described shortly. Material-based means that the deformation is captured in the material itself instead of the contact. Some of the XML elements will be addressed in more detail. Those can be either specific for characteristic or material-based, or they serve both. In this slide you see an overview of the available FEFE algorithms. In principle, you could say there are two types of contact available, either a characteristic-based or material-based. However, there are several flavors available. The characteristic-based contacts are of the type node-to-surface harm. They can be either stress or force-based. Force-based means that the penetration or the contact force due to the penetration is independent of the contact area. Stress means that the contact force depends on the contact area. Material-based, there are also more flavors available. You have the adaptive and the penalty, but besides that you have a node-to-surface, which is pretty similar to the node-to-surface harm, as you will experience in the following slides. Besides that, there is also a surface-to-surface contact available. That is basically a symmetrical contact. So the master is the slave and the slave is the master. On top of that, for surface-to-surface, it's even possible to define an edge. This is not addressed in this table, but will be discussed further. Let's go to the description. To apply an FE-FE contact, you need to have two group FEs that can be either deformable or rigid, what we call facet. As already said, you have a characteristic-based and a material-based. For the characteristic-based contacts, you have to take into account the normal direction of the two surfaces. They must be opposites to each other, because otherwise the inner surface of the contact is wrong, or potentially wrong. That depends whether it's choosing the master or the slave. The next slide, or the next slides I should say, will address the node-to-surface contact. Those are applicable for the material-based as well as the characteristic-based, but not for the surface-to-surface. The slave surface are the penetrating nodes. The master surface are the elements which generate the surface. Here you see the ideal situation. You have a smooth, or let's say less curved master surface, and the slave surface is most curved. The density of the mesh of the slave surface is finer than the master. In the next slides we will explain why this is the ideal case. Because what we say is that if there are free edges, you should take the slave. Well, what are free edges? If you have a surface which contains holes, so a non-closed mesh, or if it's not something like a volume, you have free edges. If that's the case, you should make that part or that group FE slave. If it's curved, ideally the most curved should be slave. Now let's move on to the next slides. Here you see an example of the edges. On the left side you see a master surface which is penetrating the slave surface. As the master is the surface and the slaves are the nodes, in this case there is no contact detected. If you go to the right situation, the slave are the nodes and now the most left node is penetrating the master surface. Obvious, I do not take into account in this situation the curvature. That will be addressed later on. Of course you can swap the surfaces, but you can also think about adjusting the master surface in the left side to prevent such a situation. Let's focus on the highest curvature. As said, ideally that should be slave. At the left side, on top, you see a master surface which is penetrating the slave surface. In this situation, there are no nodes of the slave entering the master surface, and for that reason there is no contact detected. Below, the surfaces are swapped. In such a situation, there is contact detected. There's another issue with curvature, which is explained at the right. If the blue, the master surface, is taken as the most curved, you will see that the forces applied perpendicular to the master surface are looking a bit strange. Probably you might expect to have something which is shown in the picture at the right bottom. That is probably the way you would expect that the forces are applied. As you already can imagine, with respect to the previous slide, that choosing a master and a slave surface can cause conflicts. It's model dependent, and those slides are just meant as a guidance to make you choose the right way. Here you see an example of a small box which is penetrating the master surface. The top picture, the forces are applied in the right direction. The lower picture, you see the situation that the small box is penetrating a lot. As you can imagine, in this situation, because it is penetrating that much, that the blue box basically is pushing out the slave surface in a direction you would not expect it, because the motion of the box is downwards. In such cases it's recommended that the small box should be slave, as it is the most curved. Mesh density is another example. At the left, you see that there is contact. On the other hand, where the slave is the most curved mesh, there is no contact detected. For that reason, we do recommend to have either similar or, if not the case, that the slave surface has the finest mesh density. Here you see another overview of the available contacts. Typically, contact between rigid structures, or if one of them is flexible, the other not, you're going to use node to surface harm. If it's more FE oriented, you will use the node to surface. That's typically if the surfaces are rather smooth, or in case like airbag unfolding, you have to go to a surface to surface. As you see, this airbag which is deploying, it's highly recommended to use the edge contact. If you're going to look in your reference manual, you will experience that there is also something like a node to surface intersect. Generally not recommended to be used, although one of the last slides we will address that there are some use cases where you could use it. Now let's focus on this node to surface harm contact, so only just the characteristic based contact. You have facet material, and you can define a gap, but it's not recommended to be used, as it makes your contact less robust. As already said, you can define a force penetration and or a stress strain characteristic. In this case, you see an example where the master is the head, the slave is the airbag, which is assumed to be deformable, and the contact type is master. That means that the deformation of the head is captured in a characteristic contact. The airbag is deforming by the material itself. Here you see a global overview how the contact is working. This is the node 1 which is moving in the direction 2. In situation 1 there is no contact detected. At situation 2 it's passing the elements, and for that reason there's a contact force generated. In principle this can move on to infinitive. Very deep penetrations are possible, which is not the case for material-based contacts, as you will experience later on. But as already said, it's better not to use a gap because it makes your contact less robust. Here you see an overview of the available contact types. This is the master, meaning that the master surface is deforming and the slave surface not. For that reason the contact surface is on, let's say, on the slave surface itself. It's good to know that the contact area, although it's master, is derived from the slave surface. So the nodes of the slave, from that, the air contact area per node is derived. The thickness, however, for stress situations, is derived from the master surface. In slave situations, the characteristic is taken from the slave. So the slave is considered as deformable and the master is considered as rigid. Again, the contact area is derived from the slave. However, in this case, the thickness is taken from the slave side. There's even a third option available, which is combined. That it can be used if they have more or less the same compliance, or let's say the same amount of deformation. Although this looks attractive, it can be a pretty high prices because it's a very CPU intense algorithm, and for that reason generally not preferred to be used. Friction. As already addressed, it should start at 0. It means that there is basically no static friction available, but it will make your simulation much more robust because it prevents numerical noise in situations where it is more or less a static situation. Under the characteristics-based contacts, you can define an initial penetration. By default, there is nothing defined. What does this mean? That in the reprint file there is no information listed, but more important, if there are initial penetrations, those will be put to 0. If you're going to define the initial type check, you will get a list of nodes which are penetrating in the reprint file. Also in this situation there is no contact applied, so the contact forces is 0. It's preferred to have the initial type master. In such situations, if there are initial penetrations, besides that it is reported in the reprint file, also the contact forces are applied. This is the most robust way of modeling. If, for whatever reason, this is not possible, you might have to use the face type front and the rel edge on. More information about that can be found in the theory manual. In short, it means that if your surface is not closed and you have initial penetrations, you might get tangling if one of the nodes is moving out of the surface. You can easily see this, for example, in your output, either by kinematics or time histories. The characteristic can be defined at several locations within the MADYMO input deck. You can define it under material null, you can define it under the group FE, or you can define it under the contact itself. The priority handling is first contact. If it's not then defined, it will look to the group FE, and if it's not defined there, it will look to the material null location. Thickness, in case of stress contacts, can also be defined at two locations. It can be defined under a property or in the element list itself. If it's defined in the element list, then that will overrule the thickness defined in the property. Now let's move on to the material-based contacts. Those, as said, are the contacts where the deformation of your structure is handled by the material itself and not by lumping the deformation in the contact characteristic like the Gar-based contacts. In those situations, the penetration has to be kept to a minimum. For node to surface and node of surface to surface contacts, you have to apply a gap. It's preferred to keep this constant in time. Within the material-based contacts, there are two contact force models available, penalty and adaptive. This example, you see an example of an adaptive, and that is also the recommended way to define your contact instead of penalty. In almost all cases, this is the most robust way to model it. As you can see, you have to define a gap. There's also something like a contact edge, that means an edge contact. It's an adaptive with some damping and a time step and a friction coefficient. If you would like to apply self-contact for the airbag, so suppose you have a folded airbag and you would like to define self-contact of the airbag, you don't have to specify the slave surface. The master surface is sufficient in those cases. The node to surface, as it said, is a non-symmetrical contact. For that, you have to consider which has to be the slave and which has to be the master surface. It's a faster calculation than the surface to surface, but you might experience contact issues. The surface to surface is a symmetric contact, meaning master and slave are swapped. If you define a contact edge, it's even possible to define contact with beams and trusses. Let's focus on the node to surface. How is this material-based contact algorithm working? Well, in principle, if the elements get tangled, the contact is lost. Well, what does this mean? Suppose you're in situation 1 and there is no contact. In situation 2, it's entering the gap and then a contact force is generated. This contact force is increasing to the third position. After that, if it is beyond the gap thickness, let's put it simple because in real it's slightly more complicated, there is no contact force applied anymore. And in this situation you have tangling. That means that the node has to generate a lot of energy to go from 4 to 1 again. The surface to surface looks at first sight even less attractive if you compare to node to surface or the node to surface Gar. Again, you have situation 1, no contact. Situation 2, it's entering the gap and a contact force is applied. If it's passing the element surface, let's put it simple, there is no contact force applied anymore. In real, it's gradually reduced this contact, because otherwise you will get instabilities. Well, this doesn't look that attractive. However, if you're going to define the edge contact, this contact will not be lost, meaning it can be at the wrong side, but it will check regularly, in principle by default 20 time steps, whether the node already has gone back from node position 3 to node 1 position. In that case, the contact is restored again. It's a very efficient, or let's say robust algorithm. I would say it's even the most robust one of all of them. And typically useful for airbag self-contact. There's one thing you have to take into account, that if you have large edges, the CPU will increase. So avoid very large edges into your contact. Now let's focus more on the contact edge. It's an optional but highly recommended option under surface to surface, so the symmetric contact. At the left side you see an ISO view of some triangles, the black and the orange one. Well, suppose the orange ones are moving downwards and the black ones are supported. At the right picture, top, you will see that there is no contact experience because the orange nodes are not making contact, for example, with the black surfaces. That's different if you have the edge contact. There the two edges are contacting, the orange and the black one, and there's no further penetration possible. As you can imagine, this makes sliding, so suppose the orange has to move from the left to the right direction, pretty easy. Whereas if there's no edge contact, the most left orange node will contact the black surface, and then it has to move upwards to, let's say, the edge location before it can move further in the right direction. You can imagine that if you have normal friction function values defined, that this will consumes a lot of energy. Contact adaptive and contact penalty are shown. Two examples. Although both are correct, the adaptive, as already said, is the most preferred one. A few things needs to be explained on the adaptive. As you can see, there is a time step defined. If you don't define it, the time step of the FE integration is used. The reason why the adaptive is preferred above penalty is because it will generate the most maximum allowable contact force without causing instabilities. For penalty, this is maybe less intuitive, and for that reason the maximum allowable contact force is too low, and for that reason you might end up more easily in contact loss. Because the adaptive makes use of the time step, the FE integration time step, the following might occur if you have a variable time step defined. The time step is due to that dropping, for example, and for that, with the same amount of penetration, a higher contact force will be generated. This might cause instabilities. For that reason, it is recommended to define the time step yourself, which is slightly larger than the FE integration time step. On top of that, it's recommended to define some damping, because that is happening in real as well. Well, some guidelines to prevent contact loss. Obvious, the smaller you make your time step, the more robust the contact will behave. As a rule of thumb, the penalty in adaptive contacts become effective below 5 to 2.5 microseconds. But that highly depends on the load case. For that reason, sometimes it's chosen for characteristic-based contacts, because those allow larger time steps, and for that faster simulation times. Well, the order of workaround in case you experience contact losses. Suppose you're looking through your animation, you say, well, this is not the way I would expect it. Well, then of course you can increase your gap, and at second hand reduce your FE time step. Because if you reduce your FE time step, your simulations will take longer, which is probably not the case if you increase the gap. Something similar can be applied to the penalty contacts. You can adjust the penalty factor, but probably even better, switch over to the adaptive, increase your gap or reduce your FE time step. If for whatever reason a simulation is required with a very large time step without contact loss, Well, as said, you can go to a node to surface har, or a more older algorithm, node to surface intersect with adaptive or penalty. You can apply a very large time step, including adaptive or penalty, but it is less robust compared to the node to surface har. Just like for the har-based contacts, also for material is recommended not to define static friction. So the values in the friction functions should start at 0. This will prevent numerical noise. As already explained in the picture of the edge contact, friction is a point of attention. If you have not applied the edge contact, it's better not to define friction or a very low friction. In case you have an edge contact defined, you can apply the engineering friction values. Initial penetrations. There are two available, initial type check or not. If you don't define it, you will get no information in your reprint file. If you define it, you get your information about the penetrating nodes in your reprint file. In both situations, however, contact force will be applied. Here you see an example. In the orange box, the initial type check is defined. Initial pen track. It's applicable for material-based contacts only. It looks pretty similar to initial type check or master. But initial pen track does the real work. Initial type check or master just provides information about nodes that are penetrating. Initial pen track on basically means that if there are nodes within the gap, those nodes will have 0 contact force. Well, let's imagine that the node is moving out of the contact and later on it's moving backwards. From that moment on, the contact is applied once it is entering the gap and not in the initial state. So it's something like resetting. It's highly recommended to use the default, because if not, you will end up with very high contact forces, because this material-based contact basically does not allow any contact, because the deformation has to be done by the material itself. The next and last slide is about the gap. As said, for node to surface harm contacts, it's not recommended to use a gap. For material-based, it is recommended to use a gap. Several ways are possible. However, it's recommended to use the gap type func. As a user, you have to define the thickness. Keep this constant and do not let it change in time, because that basically means you're generating energy. It brings me to the end of this presentation. Goodbye.